Today we're going to go over an example of proving that a function has a limit at a certain x value, or as x approaches a certain value, using the precise definition of the limit. That means we're going to need to use epsilon and delta in our arguments. I have the precise definition of limit over here to help us think about how we're applying this definition. And we're going to prove that the limit as x approaches -1 of 7x plus 8 equals 1. Okay, the definition tells us that the limit as x approaches a of f of x equals L if for every epsilon greater than 0, there's a corresponding number delta such that if x is within delta distance of a, which is this value here, then all of the output values, f of x, are within an epsilon distance of L. So let me draw a little picture to show you what this means, and then I'm also going to show you actually, I'll go ahead and show you a Desmos activity of what we're trying to do. Okay, so this is our function, 7x plus 8, this blue line here. And what we're really trying to do is, we're saying that if I pick an epsilon, which tells me this orange distance, this region, which is my distance from the height, the limit 1 here, or sorry, the limit height here is 1. So I can pick any distance from that height. And the idea of the limit is that I can then go and pick a distance from the x value, so from -1 here, where if I get close enough, all of the output values, meaning all the function values in here, are inside the orange distance from my limit. If I make epsilon even smaller, you'll notice that some of my output over here, maybe I can use a different color, some of my output here is now no longer in this window. So I have to make delta even smaller so that I can get in this window. That tells us that because epsilon can be anything, we can't really say, a specific value. But because for each epsilon, we're going to need to update delta, delta is going to depend on epsilon. So when we figure out what delta should be, it's going to have an epsilon in it, because depending on how small epsilon is, we'll need to make delta maybe smaller, depending on how epsilon can change. Okay, so how do we do that? Let's go back over to the whiteboard and see if we can get that to work. Okay, we're going to do some scratch work over here. Oops. Scratch work. And that's going to help us sort of figure out what our proof should look like. On the left here, we're going to actually write the proof. Okay. So in our scratch work, we're going to, I guess you can even say, when you start your proof, you're always going to say, let epsilon be greater than 0. So you're always just going to say, okay, epsilon exists. It's some number bigger than 0, but that's all we can say about it. In our scratch work over here, we have epsilon, and we want absolute value of f of x minus L to be less than epsilon for some x values that fall in this region, x minus a is less than delta and greater than 0. Now we should figure out what are all these pieces that we have here. Well, f of x in our problem here is just the function you're taking the limit of, so that's 7x plus 8. So when I go over here, I'm going to have 7x plus 8, that's f of x. And I'm going to say minus L, okay? L is the limit value. Okay? So in this example, that's 1. There's L. And I want this to be less than epsilon, where epsilon can be any positive number. What we're going to sort of do to manipulate this is at the end, we want something that looks like absolute value of x minus a. And whatever we make this less than, that'll be our delta. So first, let's figure out what's a. Well, in the definition up here, a is the x value that we're approaching. So in our example, a is -1. So what we're looking for So look for x minus -1 less than something. So I'll put a little star here because we don't know what it's going to look like yet. So really, if I simplify that a little bit, it's going to be x plus 1 is less than something. Okay, so we're going to look for that as we do this computation. So let's simplify this a little bit. I can write this as 7x plus 8 minus 1 less than epsilon. That's 7x minus 7, sorry, plus 7 is less than epsilon. And then I want to remember that I'm looking for this like x plus 1. That's my x minus a, where a in this case is -1. So how can I make this look like x plus 1? Well, I need to factor out a 7, and that'll make an x plus 1 show up. So if I factor out a 7 from an absolute value, I need to actually factor out the absolute value of 7, and I'm left with x plus 1 here, less than epsilon. I'm almost there. I almost have x plus 1 less than something. It's just that I have that 7 hanging out. So really what I want is absolute value of x plus 1 less than epsilon over 7. This object now, this epsilon over 7, this is my something, the star that I was looking for. Oops. So that's going to tell me that this is delta. Your scratch work is sort of backwards from how you would actually write your proof. When you write your proof, you let epsilon be bigger than 0, and then you just say this is the delta that works. So you say let delta equal epsilon over 7. That's the one that we found from our scratch work. Okay. Then for the x values that satisfy this inequality, that 0 is less than x plus 1 less than delta, which in our case, delta is epsilon over 7, we have the absolute value of 7x plus 8 minus L, which in this case is 1. We're just going to sort of recreate these computations, but I'm not going to put these less than epsilons here because that was what I wanted to happen. It wasn't necessarily like what was guaranteed to happen. It is guaranteed now because I'm going to use this fact. Okay. So we're saying let's restrict our view to these x values and see what happens with our y values. These are our y values, our outputs. Okay, so what happens with this? Well, I can say that this quantity is equal to 7x plus 7. And let me make this a little bit smaller because I'm going to run out of room here. And that's equal to 7 times the absolute value of x plus 1. Okay, now that I have gotten, I see here I have this x plus 1 here. What I know about x values in this region is that they are less than delta, which in this case is epsilon over 7. So I can say that this quantity is less than epsilon over 7, but I still have the 7 here, so that 7 is going to stick around with me. So this product is less than 7 times, so this 7 just sort of came down and stayed with me. But the less than here is because I know this part of the product is less than epsilon over 7. So I can put that here. Now these two 7s cancel out. So I have that this is epsilon. Okay. So now I have that f of x minus L. This is f of x minus, oops, I'll write that a little differently. That's f of x minus L. I did some work and I got that it's less than epsilon. Whenever x is in this region, so here's my 0 less than x minus a less than delta. Our work here was picking what's this delta that guarantees that this part happens. And it turns out that the delta that I need is epsilon over 7. That will guarantee that these output values, f of x, are within a distance of epsilon from L. Okay, and then at the end here that we say, therefore, the limit as x approaches -1 of 7x plus 8 equals 1. And then we end our proof with a little box. And this is what you would write. Okay, this would be your proof, but you should do scratch work beforehand to figure out what delta should be. Now I'm going to switch back over to the little Desmos activity that I had so that I can show you visually where this epsilon over 7 is coming into play. And hopefully that helps you maybe get a better conceptual understanding of limit. Okay, so I'm back over at my little drawing or my activity here. So let's say I have epsilon is like a 1 here, and I don't know, I'll pick a really big delta. Right now, this delta doesn't work because I've got y values that are in my delta region whose output is outside. Sorry, I have x values in my delta region whose output is way up here. So I need to make delta smaller. Smaller, something like that. That works. But what we found in our activity there was that the delta, like depending on what I choose for epsilon, the delta that's going to work will be epsilon over 7, or yeah, epsilon over 7. So I'm going to go ahead and change the definition of this delta. Instead of just allowing me to like move delta as necessary, I'm just going to say, I'm going to pick the one that works, epsilon over 7. So now you can see that when epsilon is 1, and I make delta epsilon over 7, which in this case would be 1 over 7. So maybe I'll do this first. There's 1 over 7. Okay. All of the x values in this little green region have output that is within the orange region, so within epsilon of this height. If I make epsilon smaller, like 0.884, I want delta to be 0.884 over 7. That will tell me that will be enough so that the x values in this region give me outputs in this region. Now, I can sort of automate this and say, we'll just make that epsilon over 7, which is what we did in our proof. So no matter what epsilon I pick, you'll see that the delta is also changing with epsilon, so that it's guaranteeing that my heights here stay within an epsilon distance of the limit height. So that's sort of what we did by computing what the delta value should be that will work for our limit definition. So even if I make epsilon super, super small, delta is getting so small you can't even see like the difference. You can't even see the little, there it is, the little window there. So delta is getting super small as epsilon gets really small. And how small do we need delta to get? We need it to get epsilon over 7 for this specific example. Okay, I'm going to switch back over to put the proof on the screen again so you can just look at it, see if you want to review it and make sure it makes sense to you. So here's our proof again. Remember, we did our scratch work first by starting out with what we wanted to happen and figuring out what delta should be to make that happen. Then when you write your proof, let epsilon be bigger than 0, start with your delta and x values that are between 0 and delta from your a, x minus a here. Then sort of recreate that computation. And at this step is where you're using this fact. So you replace, whenever you get to the x minus a part here, you're going to replace that with less than whatever delta was. And you'll have a factor here, so that should kind of stay with you. Okay. So that's it for the proof. Please let me know if you have other questions, and I'd be happy to help.